Time for us to do some problems involving the Cartesian coordinate system with particular emphasis here on distance and spheres. Now it's important to do problems because the more that we do, the better that we get. And especially right now, where we're just starting to develop our abilities, our skills, and importantly, our intuition. So it's important that you do as many of these as you can. So if you're following along, make frequent use of that pause button. Pause it and try the problem yourself and see how far you can get. Pretty soon, with practice, you'll be getting pretty far. You may not even need me anymore. And I'll miss you, but I'm glad that you're making great progress. All right, but of course to get there, we need to begin. So, let's begin. Our first problem. Find the volume for the set of points x, y, z satisfying 2y plus 2z minus 1 is less than or equal to x squared plus y squared plus z squared is less than or equal to 2y plus 3. Now, our first reaction is, what? Because it's not so clear what's going on. It seems a little bit different than what we may have seen before. So we got to start figuring out how to understand this and how to pull this apart. So let's focus right now on thinking about how can I think about what's going on with this expression. Now you'll notice it's kind of a long expression, and what's happened here is they've actually done something where they've taken sort of two things and merged them together, sort of mushed them together, if you will. So you should really think of it as two parts. There's this first inequality and there's this second inequality. So what we should do is break them apart and see what each one of them says. And oftentimes if we can break things apart this way, then we have a reasonable chance to succeed. Okay, so let's start with the first one, which says that 2y plus 2z minus 1 is less than or equal to x squared plus y squared plus z squared. Now, ignoring the actual inequality, the fact that we see x squared, y squared, z squared all together makes us think, hey, this could be a sphere because it is a sphere. Right, so now let's just sort of start rearranging things. Okay, so what do we have? Well, oftentimes, because we have these variables that aren't being squared, what we need to do is move stuff around to make them part of the things which are attached. Because really, we want x minus something squared, not like an x squared over there and an x over there. No. Put the x's together into a square. So let's rearrange. So I'm going to do the following. I'm going to write this as x squared, and there's no other x, so that's fine. There's a y squared, and there's a minus 2y, see, because that would come across as a minus 2y, and a z squared, and this would come across as a minus 2z. And the minus 1 I'll leave as it is. Now, let's be careful here. Which way does the inequality go? Is it a less than or equal to or greater than or equal to? And why is it greater than or equal to? Well, it is greater than or equal to, but you might say, wait, it was less than or equal to here, but you'll notice we did a quick switcheroony, and therefore we need to also flip the direction of the inequality. So this is a greater than or equal to. All right, well, now complete the square. Our goal is to make this look like a sphere, and so we need to make these terms look sphere-like. So for instance, y squared minus 2y, we say to ourselves, what would I have to add so that this whole thing here would be a perfect square? Well, negative 2 divided by 2 is negative 1. Square that is plus 1. So this would become y minus 1 squared. Of course, if I add 1, I should add 1 over here as well. Now do a similar thing for the z. Well, z squared minus 2z, it's actually very similar. And that, again, negative 2 divided by 2, negative 1 squared plus 1. And then this would become z minus 1 squared and plus 1 over here. So that, lo and behold, we have, at the end of the day, it's the same formula. We haven't modified it. We've just rewritten it, which is perfectly fine. So, what do we have? We have x squared plus y minus 1 squared plus z minus 1 squared has to be greater than or equal to 1. All right, let's see if we can sketch that. Now, what do we have? Where's our center? Well, our center would be at 0, because this is the same as x minus 0. So at 0, 1, 1. And our radius would be 1. So if we were to do a quick sketch, and we will, what do we have? Well, all right. So we have our x, our y, and our z. So 0, 1, 1 says we don't move any in the x direction. We move 1 in the y direction and 1 in the z direction. So there's our center. Our radius is 1. Okay, so it actually goes 1 in all directions. And so there we are. Now, that's the shell. The question is, what do we want? Because there's an inequality. Do we want what's inside or what's outside? The answer is we want to be outside. You see, essentially what's happening, if you take the square root, we're saying the distance has to be more than 1 or equal to 1. So we want to be outside this sphere. Okay, so just keep that in mind. We want to be on the outside. All right, now second sphere. After all, as one hobbit might say to another, sure, we've had first sphere, but what about second sphere? So let's do that. So here, similar idea. We have x squared plus y squared plus z squared is less than or equal to 2y plus 3. Rearrange x squared plus y squared minus 2y plus z squared less than or equal to 3. And we complete the square. It's actually very similar to what happened before. You say, okay, we need to add 1 here to complete that square. So that's y minus 1 squared. And we have to add 1 here. Of course, that's 4, which is really 2 squared. So what do we have? Okay, well, what we have is x squared plus y minus 1 squared plus z squared is less than or equal to, pay attention to the inequality, 2 squared. So where's our center? It's at 0, 1, 0. What's our radius? It's 2. So if we sketch that one, all right, let's sketch it. It's going to be a little bit sketchy here. So we go to 0, 1, 0, so it just moves 1 in the y direction. Okay, so there's our center. Our radius is 2. Now notice this sphere right here had radius, had radius 1. So if I go radius 2, it actually says, I'm going to be right there at the very top. And then I'm just going to go out direction, in every direction, a distance of 2. And we get something that looks something like that. All right, so where do we want to be in relationship to that sphere? Well, if we look at it, this is really saying the distance is at most less than or equal to 2. So that says we want to be inside the sphere. Now, we put these two things together. We want to be outside of the small sphere, inside of the large sphere. So what the problem is asking us is it says find the volume for the set of points. It really says, hey, find the volume for this object, which is a big sphere with a little sphere that you've taken out of the middle. Great. Now we say, perfect. Well, we just need to know the volume of a sphere. Well, we know that. I hope we know that. The volume of a sphere is 4/3 pi r cubed. So we have that the total volume, and I should say this is volume for a sphere, the total volume, well, we take the volume of the big part, so that's 4/3 pi. The big radius is 2, and subtract 4/3 pi, small radius is 1. And if we do it, well, 2 cubed is 8, times 4 is 32/3, subtract 4/3, which is 28/3 pi. Now, one thing that we should, of course, say explicitly is that the small sphere is completely inside the large sphere. We don't mind that one single point of tangency. If it had been the case that, part of the sphere was in and part of the sphere was out, hopeless with the tools we have now. Now, someday we'll have hope because we're going to develop better tools. But for right now, we did need the fact that one sphere was completely inside of the other sphere. It's almost as if whoever wrote this problem was very careful to make sure that that would happen, because whoever wrote this problem was very careful to make sure that that happened. All right, good. Well, fun problem. So in the future, if you ever see a string of inequalities like this, just keep in mind what it really means is break it up into pieces, and then you say, let me think about what each piece means, and then combine the different parts together. All right. Good problem. Wonderful problem. So let's do some more wonderful problems. Of course. Determine whether the sphere x squared plus y squared plus z squared equals 8x minus 4y plus 8z minus 20 is completely inside the sphere x plus 2 squared plus y minus 3 squared plus z minus 2 squared equals 144. So in essence, this is sort of a yes-no question. Are we completely inside or not? We got to figure this out. So we have to start thinking about, okay, well, how could we approach this? Well, let's start by looking at these two spheres. Now, one sphere is actually pretty easy to figure out what's happening. And that's the second equation here, because it's written in sort of a more sphere-like fashion. So we see, for instance, we can read off the center, and the center would be at minus 2 because it's x minus minus 2, and then positive 3 and positive 2, and the radius, well, 144 isn't just any number. It's kind of gross, right? A little bit of math humor. So gross is actually a term that means a dozen, or it's 144. But, all right, so it's not that bad. It tells us our radius is 12. Good. All right. So we know our center and our radius for one of our spheres. Now we have to think about what's the other one. Well, the other one we've got to do a little bit of work on. That's okay. We don't mind. That's why we're here. That helps us get better when we do our work. So we'll do our usual rearrange. So let's see, that's x squared, subtract 8x, and suspicious gap. Well, we know what's going to go in there. Y squared, subtract minus 4y, which really means add 4y. And then our z squared, subtract 8z, and that's going to equal minus 20. Okay, so now complete the square. So we say to ourselves, what would we need to add here? So that would be a perfect square. Well, negative 8 divided by 2 is negative 4. Square that, positive 16. So we're going to add 16 over here as well. And that makes this term x minus 4 squared. Here, 4 divided by 2 is 2. 2 squared is 4. So plus 4. Add it over here as well, plus 4. Okay, so this will become y plus 2 squared. Z squared minus 8z. Well, negative 8 divided by 2 is negative 4. Squared, 16. So add 16 over here. All right. Okay then. So we get z minus 4 squared. And then over here, you actually get a nice cancellation. The 16 and 4 combined to 20 cancels with negative 20, left with 16. All right. So, well, we can now see what happens. Our center is where? At 4, -2, 4. And our radius is 4. All right. Well, how do we answer the question now? So let's think about how we can figure this out. We have one sphere. So this sphere is the big sphere because it's what we're trying to see if we're inside that. So we have a big sphere and then we have a little sphere. And so I'll draw my circle. So maybe it's like this. Maybe it's like that. Who knows? Maybe it's like that. That's sort of our cases, right? We are either completely inside, not completely inside, maybe a little bit, maybe not. Maybe we're completely outside. Well, how do we know? How do we know? Well, one way we can think about it is we think about, all right, what does it mean to be inside the sphere? That's a good question. If we want to know if we're completely inside, we should understand what it means to be inside. Well, it means that all the points on the smaller sphere should be at most the distance away is the radius of the larger sphere. So what we can look at is ask the question, well, what's the furthest away my small sphere can get from the center of the large sphere? So we say, aha, what we should focus on is we start at the center of the large sphere. Let's say that's the center of the large sphere. And we say, what's the worst case scenario? In other words, what's the furthest out you can get? And once I know that question, then I can ask the question, all right, is the furthest point away within my radius of the large sphere? So now we ask ourselves the question, how can I get all the way out to there? I think you can see that going from the center of the small sphere to the furthest point away from it on the large sphere, we cross over an interesting point. Right there. It's the center of the second sphere. So now we have an idea which says, all right, let's figure out the distance between the centers. Let's look at the distance, that's the radius of the small one, and now compare that to the radius of the big one. So we need to do some distances. So let's start with the distance between the centers. All right. Well, what are their centers? Well, we have them written down. They're -2, 3, 2, 4, -2, 4. So the distance between the centers would be what? Well, take the difference. 4 subtract -2 would be 6. So we're going to have 6 squared. -2 subtract 3 would be -5 squared. 4 subtract 2 would be 2 squared. So that's the square root of 36 plus 25 plus 4. Or, if you like, that's the square root of 65. Ah! I wrote 64, but I did say 65, so there we go. Square root 65. Now, here we go. We wanted to compare. It all boils down to this question. We're going to take this distance between the centers, the square root of 65, add to it the radius of the small one, 4, and now what we want to do is compare this, we don't know how it compares yet, to 12. So, here's the thing. If this is a less than or equal to, then we're all inside. If this is a greater than, then at least some is on the outside. So now we have the question, well, how does the square root of 65 plus 4 compare to 12? Now you notice I had a little bit of a slip a few minutes ago. That was unintentional, but let's take advantage of it. I wrote square root of 64. What is the square root of 64? It's 8. How about the square root of 65? Well, it's a little bit bigger, right? It's 8 and a bit. So this is 8 plus some small amount. I don't know exactly what it is, but it's 8 plus a small amount. And we like epsilon to represent a small amount, plus 4. Well, what does that say? Well, what it says is that the distance between the centers plus 4 is just a little bit bigger than 12. Not much, small amount, but it is bigger than 12. So that says this is the right kind of picture. We're just barely sticking out. Not by very much, but we are sticking out. So are we completely inside the sphere? And we can now say the answer is no, we're not. But again, it's not so obvious. It would, because of it's just only a little tiny fraction is outside. You would have to be really careful on how you drew the spheres to figure it out. But of course, you don't have to draw the spheres to figure it out. We can use our intuition, our geometry, and talk about distances. Because when you start about spheres, at the heart, it's all about distance. All right, good. Good problem. Good problem. Okay, well, let's try another problem. Find an equation for the set of points x, y, z, where the distance to the point 1, minus 2, 4 is equal to the distance to the plane z equals negative 2. And give your answer in the form of z equals some expression in x and y. That's oftentimes how we like to have our answers, z in terms of x and y, especially as we go on and sort of towards the middle and then end of the course. We really like to think of saying, well, how does z change as you change x and y? So we like to have it where z is a function of x and y. All right, so how do we begin this problem? Well, in some sense, this is our chance to practice translation, where we have something written out language and verbally, and we want to take it and say, okay, let's rewrite it mathematically. It's a formula that we can work with. So how do we do it? Well, let's start translation. So we're learning to translate, from English to math. Okay, so here we go. So find an equation, that's what we need to do, where the distance to 1, negative 2, 4. Okay, well that is something. There's a definite formula that says, hey, if I have x, y, z, and I have 1, negative 2, 4, here's the formula that connects them. So let's write that formula down. So that would be the square root of x minus 1, quantity squared, plus y minus 2, so that's y plus 2, quantity squared, plus z minus 4, quantity squared. Okay, distance between the points. All right, keep translating. Is. Aha, is. That also means something. Is, here, really is corresponding to equal. In fact, we say is equal to. So when we see something like is or equals, we say, okay, equal sign. Good. Now, the next part we've got to translate. It says what? Well, distance to the plane z equals negative 2. So let's think about what's happening here. So here I have my point, arbitrary point, x, y, z. So there we go, that's x, y, z. Now, there's something called the plane z equals negative 2. What does that mean? Well, it's all the places where z is negative 2. So what you do is you can start with the xy plane, which is z equals 0, and it's like you push it down. And so there's this z equals negative 2. It's like you push the floor down two rungs. Okay. So what's the distance here? Well, we can think about it in a couple of ways. I mean, one way we can think of it is say, well, look, if I really want to have the closest point to x, y, z, where the z value is forced to be negative 2, then that would be x, y, negative 2. All right, and then you can find the distance between them. But the other thing is to say, well, really, the x, y don't matter. The question is, how far am I off in the z? So how far is it to go from my current z value to a value of -2? And the answer is, you take a look at the difference. So z minus -2, that's the difference between a coordinate and that point x, y, -2. Okay. Now, difference, I'm being very careful here, is not the same as distance. What's the difference between difference and distance? What's the distinction? Difference has a sign. I can move positive or negative. I can increase or decrease. Whereas distance is a measurement, and it should be positive. So since we want distance, throw in some absolute values. All right, good. We've done our translation. We said, aha, we're really looking for an equation that comes from this, where the distance from our point is equal to the distance to our plane. Good. Now we have it set up. We're not done. What do we need to do? Well, we have to follow the instructions to give our answer in this form. Yeah, so we have to rewrite it so we get z equals something, which means algebra. Woohoo! We love algebra. This is great news for us. Ah, nice. Just when you thought we wouldn't get to do any more algebra, it comes back in. Okay, so, well, what do you want to do? I don't like square roots. In fact, it's a personal weakness of mine. I often try and look for ways to get rid of square roots. Now, of course, there's good ways to get rid of square roots and bad ways to get rid of square roots. Let me mention, and I'll say it many times, the bad way to get rid of a square root is to say, oh, the square root of a squared plus b squared, hey, that's just a plus b, right? Right? No, this is so wrong. Oh, every time a student writes that, a calculus teacher cries a tear. It's just, I know a lot of people write that, but the thing is that it really comes down to the fact that addition and multiplication don't mix so well. So you got to be careful here. And you might say, well, what do you mean by multiplication? The square root really is about taking something to a power, and that really involves some sort of a flavor of multiplication. So, okay, so we can't get rid of the square root that way. Well, how do we get rid of the square root? Well, a great way to get rid of it, if we have a formula where something equals something, is to say, well, let's do something to both sides, which gets rid of the square root. In this case, we square both sides. So, squaring both sides, we have x minus 1 squared plus y plus 2 squared plus z minus 4 squared equals, and here, the absolute value squared, well, the absolute value won't make a difference if we square it, so write as z plus 2 squared. Now, because I don't see any other x's and y's, I'm not going to do anything to those terms, but I do see z showing up in two places. I'm going to expand the z parts. So, z squared minus 8z plus 16. That would be what happens if we expanded the left-hand side. Over here, z squared plus 4z plus 4. And now, we're like, good news. Great news, actually, because we can see some cancellation. The z squareds go away. Well, what's left? Well, what's left is we've got to move some things around. So let's move the minus 8z one way, and we'll move this 4 in the other way. So we get the following. So this would become a plus 8z, and there's already a 4z there. So that makes 12z. So 12z equals this piece. We have the x minus 1 squared plus y plus 2 squared. And 16 subtract 4 would be 12. Oh, that's kind of nice. Now, we need to get to z equals. We're really close. We have one single z. That's a good sign. Our problem is it's not just z, it's 12z. So we got to get rid of the 12, but now we use our technology called divide. So we'll divide. So divide everything by 12. Everything gets divided by 12. So we get that z is equal to, write as 1/12 x minus 1 squared plus 1/12 y plus 2 squared plus 1. And there we go. That's it. That's the formula. So we've said, aha. So when we have our set of points which are equidistant from a single point versus a plane, it has sort of this interesting flavor. Now, in case you're wondering, what does that look like? We don't need to know it to answer the question, but this looks like what we would call a bowl. And and in particular, if we had the point 1, -2, 4, let's say it's here, and here's our plane, what would happen is that the very bottom of the bowl would sit halfway in between the point and this point in the plane. That's not too surprising. And then it would sort of work its way up. So that's the shape that's being formed when we talk about the points which are equidistant from that point and the plane. Again, we don't need to know that to answer the question. We really just have to say, hey, let's look at distances and let's solve and clean it up. So there we go. All right. Good. Good problem. Good problem. All right. Well, that leaves us with one more problem. So let's finish up on a high note. Find the value, or maybe values, so there might be one or several answers, so that the two surfaces, x squared plus y squared plus z squared plus 1 equals a squared plus 2z, and x squared plus 4a squared plus y squared plus z squared equals 4ax plus 2z, intersect in a single point. Interesting. Different. Well, that's great. It's wonderful to see a different type of problem. It means that we get to think about it. So, what do we have? Well, first off, let's talk about what these surfaces are. Do we recognize them? Well, when I see the x squared, y squared, z squared combination, so they're all on one side, they all have coefficients that are equal, that says to me sphere. It also says to you, right? You can almost hear it. If you lean in close, it's whispering to you. We're becoming the calculus whisperers. It's going, sphere. Did you hear it? Listen close. I'm a sphere. Yep. Okay, I heard it that time. Okay, good. All right. So we know what we're dealing with. We know we have spheres. So let's clean it up and actually make them look like proper spheres. So that means doing a little bit of rearranging, completing the square, all the good stuff that we do with these types of expressions. So let's label these. I'll label this as 1, label this one as 2. So for 1, what do we have? Well, let's move the 2z across. And it looks like, because it's only the z that doesn't already have it completed. So we have z squared minus 2z plus 1. This is already a perfect square. Wow, nice. They already got it for us. Okay, so that equals a squared. All right. Good. Now, let's talk about the center. The center, what is that? Well, it's at 0, 0, 1. Now, right, 0, 0, 1. And the radius, okay. This is actually a little bit subtle here. What's the radius? Are you sure? I'll give you a second to change your answer if you want. All right, so here we go. The radius, the natural thing for us to look at this and say, ha, the radius is a. But why is that wrong? Radius is a measurement of length. Now, what do we know about a? And right now, the answer is we don't know anything about a. We just know it's a value. A could be positive or negative. So I can't have a negative value for my radius. So what's the correct value for the radius? The answer is, well, whatever the size of a is. So it's the absolute value of a. So it's another way of saying it is the square root of a squared. Well, the square root of a squared is the absolute value of a. Okay, good. Well, I wonder if that'll come into play. It might. It might. Okay, so now let's go to number 2. And we'll do something similar here. So let's see. We have x squared, subtract 4ax. Now let's think before we write down the next part. What would we need to add? Well, divide that by 2. It would be minus 2a squared would be 4a squared. They gave it to us. Wow. These people who write these problems, they really want us to succeed. Okay, so y squared, z squared. See, there's no other y, but there is a z, so we've got to move the minus 2z equals, and currently it's 0. Now, we do need to complete the square here, so that we would add 1, because negative 2 divided by 2 is negative 1 squared, 1. Add 1. So this is a nice square, z minus 1 squared. This is 1. By the way, 1 is also equal to 1 squared. And then this, of course, x minus 2a squared. Let's go ahead and throw in the middle term. Okay, so now we see it. Our center is where? Well, it's at 0. Whoops, not 0. 2a. 2a. 0, 1. There we go. And over here, our radius is 1. Good. Now, so far we've figured out our center and radius of our two spheres. Now we have to ask the question, okay, we want them to intersect in a single point, which means they have to overlap, but just barely. They're just barely touching. So the question becomes, how is it possible for two spheres to touch at one point? Well, one way to do it is you can think of it like as a snowman type configuration, where you have one sphere and then another sphere. And then they just barely touch. Is there any other way that you can have two spheres touch at a single point? Well, the answer is yes, because we can also have one sphere nestled inside of another sphere, but they just touch at a single point. So again, in both cases, they just touch at a single point. Okay, so now we have to start thinking about what's true. So let's talk about our two possibilities. So if we look at our first configuration, the snowman type configuration, I think is definitely the more intuitive one. We can look at it and say, I see how it all fits. So what we can do is we can say, well, in the snowman configuration, if we look at the centers, what's true is that the distance between the two centers has to equal the sum of the two radii. So if we think about our distance, well, let's talk about our distance. What is our distance? We see, okay, the z coordinates and the y coordinates are the same. So our distance between centers, we'll make a little note here, distance from our centers is going to be what? Well, it's going to be the square root of 2a quantity squared, and so it's 2 absolute value of a. Okay. So what we need to have is that here we need to have it be the case that when we add our distances together, when I talk about our distances, I should say our radii, the radius of one circle plus the radius of the other circle, it has to be the same as the distance between the two centers. So we need to have that 1 plus the absolute value of a, the sum of the two radii, is equal to 2 times absolute value of a. Well, subtract 1 has to equal absolute value of a, or we come to the conclusion that a should be plus or minus 1. All right, good. Are we done? No, right? Because what else do we need to do? The other thing we have to do is look at the other possibility. And this one we have to be really a little bit cautious about. Okay, so how do we handle the non-snowman? Well, we'll do something similar here, which is we'll look at the distance between the centers. So the distance between the centers, what's true? Well, we'll write down our distance between centers, 2 absolute value of A. We have to sort of think about, how could I get from one center to the other? Well, here's what we can do. We know they have one point in common, so let's think about it in terms of that one point. What we'll do is we'll go out from, say, the larger one to the common point, and then back the smaller radii. So see, we're going forward the big radii, back the small radii, which means we're doing what? We're looking at a difference. Okay, so in other words, we need to do a subtraction. So we're going to look at 1, subtract the absolute value of A, and take the absolute value of that. That has to equal the same thing as 2 times the absolute value of A. Okay, all right. Now, there's a lot to parse here. Now, how do you get rid of an absolute value? There's 2 possibilities. It could be the case that 1 minus the absolute value of A is a positive expression, and the other case is 1 minus the absolute value of A is a negative expression, and you just explore those 2 possibilities. So let's suppose 1 minus the absolute value of A were a positive expression. Then the absolute value doesn't do anything. You get 1 minus the absolute value of A equals 2 absolute value of A, or you move that across, 1 is equal to 3 times absolute value of A, or absolute value of A is 1/3. And now we say, aha, well, if the absolute value of A is 1/3, we can get the conclusion that A is plus or minus 1/3. So there we go. Now, the other possibility, and we do have to check because it truly is a possibility, is that the inside part here was negative. So it means I need to flip the sign. So if I flip the sign, that becomes negative 1 plus the absolute value of A has to equal 2 times the absolute value of A. Well, if I move that across, that says negative 1 has to equal the absolute value of A. Well, wait a second. I can't have the absolute value of anything be negative. Absolute value it's a measurement. It's always greater than or equal to 0. So this says, look, not possible. There's no solutions. So now we've accounted for everything. We looked at the 2 different ways that the spheres could be configured with each other. We looked at all the possibilities that they lead to, and we end up with 4 different answers. So the 4 possibilities for A are, we'll put them all in one list. There's 1, minus 1, 1/3, and minus 1/3. And that is the answer. Wow. Cool. Beautiful problem. Beautiful problem. That's a little bit subtle. So much to the point that when we first did this problem many, many years ago, we actually didn't quite get the right answer in the solutions. So we had to go back and redo it because you got to pay attention. You got to keep track. And this is the part that it's easy to forget about. So you have to pay attention. Well, that's why, don't rush. Think about things. Have you accounted for everything? Are you sure? What are some other possible ways that things can happen? You see, sometimes it's easy in math to say, oh, here's a nice configuration, so that must be it. But you got to make sure it's like, is there another configuration? Is there something else I'm overlooking? And so you have to be open to more possibilities. But that's not a bad thing. Being open to different ideas, different possibilities, it's a wonderful way to approach life and also to do math. All right. Well, thanks for coming to our practice, and keep up. You're doing great.